noise. Uh, just requesting you to not struggle to unmute yourself in between. We would also love to have your comments and questions, but in order to have an uninterrupted presentation, we would request you to put your questions in the chat portion of the screen anytime during the presentation or right after. We will be monitoring the chat and will pose the questions to our speaker at the end of the presentation. Today's webinar will be recorded, so we will be able to share a link with you sometime later this week on our website. We welcome you to revisit the content yourself and share it with your colleagues. Before we begin, just let me tell you a little bit of ASEI. We are the American Society of Engineers of Indian Origin, an organization of engineers and technical professions, obviously from the Indian origin. ASEI was established in 1983 in Michigan and is a non-profit organization. Since its inception, ASEI has strived to institute a channel of communication between technical organizations within the United States and abroad. It has also provided assistance to engineering students at the local and national levels and lent a helping hand to charitable organizations, besides organizing monthly networking events. Moving on to our webinar, which is about the rise of computing in the automotive DNA. Like I mentioned, it's basically in future, what are you going to do with your car? Are you going to take it to a mechanic or are you going to take it to the IT department? That is the question. So the growth of electronics within the automobile has been nothing short of phenomenal. The talk will focus on many of what is the under the hood computing portions, technologies, and the accompanying massive software stack that needs to go with it. To give us a deeper insight on the subject, we have with us Sharan Kalwani. He's a high-performance computing specialist and consultant. His responsibilities include active participation in several initiatives, helping users harness the power of HPC towards solving many of the world's tough problems. Sharan brings a high degree of engineering, industrial business, and strategic value perspective towards greater adoption of use of HPC in many facets of our life. He is the 2017 to 2020 chair, IEEE Education Society, and vice chair of IEEE Computer Society's local chapter. Over to you, Sharan. You can share your screen. Let me just make sure that, and we do want to mention we have an upcoming webinar series next week, same time, same day, and the week after too. And hopefully we'll continue that. So look out for that, stay tuned. Yeah.
Okay, thanks for the invite and talk today. So I do have an awful lot of material, so I hope you can bear with me because the subject matter is such that I would like to, shine a light on many of the aspects that many folks perhaps may not be aware of. So the title is actually quite apt. What I call as the modern day automotive DNA is basically every facet of the car. We've seen computers invade that territory. And to understand this, we'll also, look a little bit on the history of the entire thing. Some of the areas that I'll cover are basically, electronic control units and safety systems. They go hand in hand. Then the so-called infotainment that actually was the second stage of computers, entering the automotive space. And then with smart cities and interconnection that people want, it was natural for transportation to start talking to each other. Doesn't matter what kind of transportation it is, but cars are certainly a very large part of it. And then more recently, these so-called self-driving technologies, that's actually been perhaps the biggest intrusion. And I use the word without intending a pun there, intrusion of computers in the automotive space. But what I will also highlight is a few areas that people forget about or tend to overlook. So as you can tell, there's quite a bit of stuff that we'll talk about here. Okay, so how did we actually end up out here? Well, it's pretty easy. We don't have to go very far back. Around maybe like the mid 60s, Volkswagen in Europe, they came up with the idea of what they called an engine control unit because they wanted to be very precise in doing electronic fuel injection. So their engineers, they spent about 3 years creating that stuff. And here on the right-hand side, you can actually see this was a full-page ad that was shared in a magazine, I believe called Popular Mechanics or Popular Science, I forget which one. And you see, they called it the electronic brain. And of course, it is smarter than a carburetor. I won't say smarter, but I would say certainly faster than a carburetor, because in a carburetor, it's an analog device. There's always some lag, whereas this could respond within milliseconds to the drive conditions and supply that. So it looks like, a little board, controller, electronics, and they made a big deal about it, and people actually liked it. So they started equipping more of the cars. Well, it didn't take long before other manufacturers said, we want to do the same thing as well. And there was a whole bunch of people doing it. Maybe about 5 years later, General Motors started using a microprocessor in their Buick vehicles for engine controls. There are a lot of other things that GM did, but I only wanted to highlight this simply because of the electronics part. And those of you who know computers should not be surprised that it was a tiny 4-bit microprocessor. Today, most of the microprocessors you have in your modern day laptop are 64-bit. So several orders of magnitude powerful, but that's where they got started. And then from 4-bit microprocessors, they went to 8-bit. And you might also remember a company called Delco Electronics. I don't know what they're called these days, but I'm certain the people around, they just have changed the name. And then in the 80s, they went to 16-bit microprocessor controller chips, and many others did it, your Fords or Chryslers. And then, the engine control unit, or the ECU, became a pretty much standard part of the engine at that time. Now, I've included some links out here at the bottom. You can always check them out in the recording later if you do want to follow up about it. Well, starting with engine control units, pretty much we've invaded every space of the automobile. This is a real example. I think I took it from an SAE publication. As you can tell, your engine control unit, that's right out here. Now, if you go clockwise, you'll see automatic braking, power steering, throttle control, onboard diagnostics, idle start and stop. I actually find that a little annoying because it stops at a traffic light and then it suddenly changes and then it starts up and startles folks out there. And then so many things, even electronic stability. You go this entire circle out here, and each one of these has an ECU, no longer an engine control unit, but an electronic control unit. Lucky for them, engine and electronic both start with the letter E. So that acronym has survived. Therefore, it gives you an idea of how much computing has become practically pervasive. And we'll come back to this in terms of what somebody earlier mentioned when joining this meeting was, entire hardware, software stack. So that's a key part out there. But I did want to mention that not just the engine control unit, to basically have precise fuel and fuel air mixtures and stuff like that. But if you recall, safety was a very big feature. Seat belts and all were just one aspect. But they started putting in electronic control units that could handle the braking, the stability control, the cruise control, and many things. So if you just take a look at this, in 2006, there were approximately about 13, electronic control units, like the anti-skid braking system or the PCMs and stuff like that. Then in 4 years, this practically doubled. It actually became 26, which is, of course, quite a rise, a doubling in just 4 years. And then in 3 years, from 2010 to 2013, this actually tripled. What caused the tripling? Well, what we call the human machine interface, the dashboard where you have all those fancy controls to connect your Bluetooth or phone and stuff like that. They're all little computers inside there. And now in 2020, it's actually documented that you can get one of the high-end luxury cars, for example, the Mercedes Maybach. And when they did a count of the electronic control units, it was well over 100. I don't know, like 103 or 104 that's out there. So clearly, from a modest one ECU back in 68 to 13 to 26 to 65 to 100, and we're not sure where it's going to stop. Probably, who knows, another 10 years from now, it could even double to that number. So it's quite a rise, quite a growth in that. But what sort of accelerated this was all those safety systems. So here's an example of a safety system where there's a microprocessor control unit in the center. Then it's got all these sensors like spark plugs and all sorts of other things, fuel injectors. Then they have these chips and an internal computer network like CAN, the Computer Automotive Network, that are controlling many of these other computers that are working with these actuators. And all of these, you can tell that it's very, very complex. So in order to function these complex systems, they had to introduce more and more computing. And just a single microprocessor was not sufficient at all. They had to go to multiple microprocessors or microprocessors that had multiple CPUs embedded in them. I'm sure if you've gone to Best Buy or Micro Center and looked at laptops to buy, the guy will tell you, oh, this has got 2 cores, 4 cores, or 6 cores. Well, they're all multi-core systems. And we need them in our safety systems because no matter how fast a single core is, you saw in the previous slide how many complicated systems it has to handle, and it takes time for it to respond. And single core microprocessors are no longer getting faster. So what they have to do is add more processors in order to do same amount of work, or have one processor respond to things, another processor monitor things, another processor do things. And the more the processors you have, the more the electric power consumption. And the more the electric power consumption, you're going to have heat generation. So it's really, lots of issues at the same time. But multi-core is the only way that they can solve this. I just put a little math out here because the more the clock frequency, the more the voltage you have to draw, and all of these play a role. If you just had a single core processor and just kept the frequency the same, it wouldn't cut it. But if you went to multi-core, you could get actually more than 1.88x improvement without sacrificing performance or power. So this is why more cores that they are in ECUs, then there's going to be more software as well. And we'll come back to that again. For safety systems, it is very important that the software works as it's required, and testing it is a very complex issue. However, it does give a lot of flexibility. because when you have more compute power at your disposal, you can try a lot of different software. You can have one software that's running in the car, that's production, another one that's updating it at the same time, or you can test out without compromising it. Or if maybe the main software module fails, you can have a second backup module because you have more than one core available, take over the job. So it does free up the engineer to do a lot of things. And if you're interested in more details, I would recommend that you actually check out the newer version of AutoSAR. I forget how they did the naming of it, but I do know it's called AutoSAR Adaptive. And combined with that, this ISO 26262, which deals with a lot of how to validate all of these things. So that's just one area, and we've seen dramatic complexity increase, and with that complexity, more rise of computing up there. Now, let's talk about the second aspect, which is your in-vehicle infotainment, sometimes abbreviated as ISI. So I was for a long time in Michigan and worked in many areas. And then in 2009, I took an opportunity outside. And I came back 3 years later. And then everybody I met, they were all talking about, oh, we've got to deliver on infotainment. And you'd be surprised that they were hiring literally hundreds of people. And what was infotainment back then? Basically, I'd like to plug in my music. I need Wi-Fi inside the car. Can I access the internet? I need dashboard apps and stuff like that. So that's the kind of thing. As you can tell, every car has their own way of doing things. And clearly, it was not just hardware and software. They also had to hire people who understood how humans behave, how humans think, how do they respond. And there was constant churn and turmoil. Each one of these is kind of state of the art, but they all look very different. And clearly that actually, I think, indirectly leads to more brand loyalty, because once you buy a car, you get used to the infotainment. You don't want to learn yet another way of pressing buttons, but you say, all right, I'll stay with the same model car, maybe the next 3 years later. At least I know how to operate the dashboard out there. So forget driving skills. This itself became quite a challenge out there. But here's a little survey from IHS Automotive. You probably have heard of them. They have a pretty big office in Southfield. I forget which one of those black tall towers, but at the top is IHS Market. They shared this little information with me as to what is it that people want in their infotainment, the touchscreen for entertainment, navigation, and vehicle information. It's more than 50%. And then very close behind that is we want automatic Bluetooth for hands-free calling, which is good. It's a safety feature as well. But look at all of these little high-speed wireless internet, heads-up display, an audio system, use my smartphone with the apps and stuff like that, stream my Bluetooth. A lot of these are now pretty much in there. And so I have to go back and ask them that, what's new in this space? And I'm sure they'll come up with even some more wild stuff, most likely in the automotive driving. Now, this is not just US based. This is actually both US, UK, Germany, therefore Europe is covered, and China, which are the largest car markets. So you can see pretty much everywhere people want the same thing. As a matter of fact, if you look at some of these, the Chinese consumers are even a lot more demanding simply because they're a lot more smartphone penetration and savvy. So they want a lot better integration. So this has caused a lot of electronics and a lot of software to enter this space. So safety ECU was one, then in-vehicle infotainment was the other. This is just a list of what else would it control. All the audio, the navigation, the telecom, the climate control, separate entertainment for people sitting at the back, in the front, Voice processing, that's a new area where you want to say something and it has to adapt to your voice so that it can recognize it. This is where you might hear the term NLP, or natural language processing. For many years, this was the domain of artificial intelligence. And now it's being added on as a module so that you can train it for your voice and then in different languages as well, so that it can actually do things without you having to punch 50,000 buttons there. And by the way, if you like to know more, there's a magazine published by the IEEE called IEEE Spectrum. They regularly, every 3 to 6 months, have very in-depth articles on each one of these aspects out there. And then, of course, in order to deliver all of this vehicle and infotainment stuff, we have to have embedded sensors, because it has to recognize your voice, cancel out the noise. It also has to have built-in GPS devices. It has to have haptics, which is a term for when you do a pressure-sensitive finger touching or with the stylus and things. I mentioned NLP before, and it also has to have computers and software that can handle the Wi-Fi and maybe also talk 3G, 4G, and nowadays 5G and LTE as well. And then to do all of this, we need also separate software for the human-machine interface so that it can present natural choices, make it easy for you to navigate through all these complex systems, or easy to use. If you want to make it easy to use for the driver or passenger, then you have to put a lot more software, a lot more code, a lot more boundary conditions inside the software that'll run all of these other things. And then finally, the latest thing, connected car. You recall I mentioned that with smart cities and transportation systems, they want to talk to each other. The whole idea is to have optimal use of resources. So connected car itself is a pretty big activity. I don't know how it's changing, but I expect that it'll continue because there's still too many people involved, cities, municipalities, federal and state, and at least in the United States, we don't seem to have one single uniform authority. In Europe and China, they seem to have a little better handle on that. So what does this mean? When you don't have a uniform regulation, it makes the software even more complex. So there you have it. So again, those mobility apps, they're just about there for everything. And sometimes these mobility apps are not in the car itself, but it's in your phone. So maybe an automotive supplier, or they have to build all this stuff. It has to work with all the built-in stuff inside the dashboard and navigation system, talk to external apps, or maybe talk to a cloud. Maybe it also needs constant software updates. And over the air, OTA is becoming more and more prevalent, at least with some of the newer cars, but they come with their own issues as well. And there's a problem too. We still have a lot of cars out there, easily 100 million, at least in the United States, that don't have many of these infotainment built-in electronics and systems. And we're going to have for a long time a mixed technologies out there. And of course, to make all of this thing work, you can't satisfy everyone. Everyone has their tastes, likes and dislikes. And I remember at an automotive car show back in January, I could hear several people, a crowd, when they were observing a minivan, which was still the rage in those days, saying, "Oh no, I won't buy that." And the person who was at that exhibit asked him why. He said, "Your cup holders are too small or too few." So people base decisions on things like that. I wouldn't be surprised if they don't like the dashboard and say, "No, we're not buying it because the dashboard is too complicated." So it's quite interesting and surprising. So moving on, here's a little picture. By the way, that particular car is a hybrid Pacifica. And this illustrates just the wireless connectivity that it has to have. It has a ton of cameras, a ton of Bluetooth sensors, GPS sensors, Wi-Fi harness, the radar, RFID, and then antennas so that it can try and catch a GSM or LTE signal. And it has to talk to nearby cars or devices that you brought in, detect that, and do Bluetooth. And then, of course, the car itself probably has to talk to some cloud, either using your smartphone or even talking to your smartphone to the cloud. So just this itself shows you that the modern day automotive engineer, he can't call himself, oh, I'm a body in white guy or a chassis guy or transmission guy or powertrain guy. A modern day automotive engineer can say, oh, I'm a camera guy, and I'm working in automotive systems or GPS, and they may know nothing about the transmission or fuel air mixture. So next time you meet an engineer and say, hey, you work for so-and-so, can you help me with my car? Expect they'll say they know nothing about your car, but if you want to fix the GPS, yeah, we can help you there. So let me extend on that connectivity theme a little bit. This is a graphic from the US Department of Transportation. And this is the vehicle or smart city or connected car that they're talking about. As you can tell, this is a modern day city where you have vehicles crossing all over. They need to talk to either central or distributed resources. They need to be talking to other vehicles on the road. They need to be talking to transportation systems like rail or bus systems. They need to talk to traffic lights as well out here. So all of this is a part of that connectivity. And it does have an acronym, which is called V2X, vehicle to X is anything, X is like your algebra, unknown variable, talk to everything, vehicle to infrastructure, vehicle to transport, vehicle to city, whatever the case may be. And this itself is quite a challenge. And there are only a few cities in the world that have implemented something that is close to this. I seem to recall in China and Singapore, they've got systems set up, but you won't find it very prevalent yet, simply because what I mentioned, that the state, federal regulations are kind of all over the place on this. But just to illustrate what is involved inside of this, they want these vehicle connectivity to actually be able to do e-payment or communicate with other cars with safety messages. For example, this is my speed and I'm slowing down or I'm speeding up. They want the vehicle to communicate it to all surrounding vehicles. Or the V2X, where here X is the infrastructure. And we have one example right here in Michigan. It's called M-City. I believe it was set up in the Ypsilanti part of the old Willow Run. And it's run, I think, by folks from the University of Michigan. They want the vehicle to talk to the traffic signals, talk to the smart city, so maybe it can find parking and stuff like that, or even share vehicle data that on such and such vehicle, this is my fuel, this is what I'm looking for, or geolocations and things like that, or driver assistance. So the vehicle can talk to other vehicles for maybe updates on locations and things like that if it loses its satellite signal and things like that. And then there's more people that they've set aside things in the V2X standards work so that it can take care of things that we haven't yet encountered later. But that's a lot of future work. And again, it's ongoing, but what's the point here? All of this needs computers and software, so it's only going to grow. These are just a little acronyms that I wanted to share. I mentioned V2V as well. There's also V2P, vehicle to pedestrian. So if there's someone with a smartphone walking and not paying attention, it can actually alert and say, you better look both sides of the road before crossing and don't stare into your phone, you might get hit. And then vehicle to network, for example, traffic lights, and then vehicle to infrastructure as well. So just some of the acronyms, it's all covered under V2X, at least for today, until they run out of alphabets up there. Okay, so now the fourth area, which is one of my favorite areas, the autonomous vehicles. And I don't know, some of you might have seen something like this kind of car, which has this sort of rotating thing on the top. This picture, I got this from, I believe, somewhere in Pennsylvania where they were running these tests. And if you talk to the locals there, they call this, oh, yeah, you mean the car with the Kentucky Fried Chicken bucket on top? Yeah, we know what you're talking about, because that's what it looks like. This is actually the radar or LiDAR that's bolted on top of a self-driving car. And this is one of Uber's experimental, and I think you'll find the same in Phoenix and a couple other cities as well. Here's a picture of a self-driving truck called Otto that I believe the German car makers or maybe one of the European Swedish car makers, I forget. But you can see there's a person sitting at the side monitoring this, but the truck is driving itself along a well-known path. This is an inside look. Yes, it was Mercedes that came up with Otto, the self-driving diesel truck. And the driver's sitting out here monitoring a lot of stuff, but he doesn't touch the steering wheel. It's driving itself along preset patterns. So this is the fourth area where computers have made an even accelerated, how should I say, pervasiveness in the automotive structure or the automotive DNA, if you will. And it's quite a complex area. So I don't know how many of you are familiar, but I will share this briefly. There's no such thing as, oh, is it self-driving or not? We actually have varying degrees of self-driving. And the SAE has actually defined this. You can get the document which describes all of this. You can download it for free. So they divide this into about 6 levels, starting from level 0 all the way through level 5. Clearly, level 0 is, there is no electronics which is running the driving of the car. It's actually a physical person. So that's level 0, which is all the cars which we probably bought before 2000 or maybe in 1995. Level 1 is where there's a little bit, we call it more assisted driving, where it's still the driver's in charge, but there might be some small task in a very defined use case that the computer is performing. For example, maybe cruise control or adaptive cruise control, or maybe keeping inside the lane. And then there's level 2 where there's partial automation, and I'll share a little bit about that through a video in a few seconds. Here the driver still monitors, but there's active driving done by a system. So it's performing both longitudinal, means straight ahead, lateral means sideways, again within a well-defined way, but it's doing that. And then between level 2 and 3 is sort of like this, what I put here as a dotted red line. It's actually a gray area. You'll hear many automotive manufacturers claim, oh, we're level 3 or level 4. Don't trust them. That doesn't mean anything. They might take one tiny feature, level 3, add it to an existing level 2, and call themselves level 3. I've even heard of manufacturers or car companies saying, oh, we're level 2.5. There's no such thing as level 2.5. It's all marketing that they invent. The whole idea is that they want to appear very, state of the art in automated driving, because that's where they see the future. But level 3 is conditional automating, where the driver doesn't need to monitor the dynamic driving task, but can override it at any time they like. And then level 4 is a very high level of automation where the system is doing practically everything. The driver is not required. So we're still many years away from that. And level 5 is full automation. This is the kind of thing you see in science fiction movies where they just get in, read a comic book and tell the car, you know, take me to headquarters, and they don't pay attention to anything except, you know, talking to their friends, and the car does everything. So that's level 5. And so we're still quite a ways away from that. So today, this is where we are, sort of between level 2 and 3 in most cars out there. So how do they achieve this? Well, clearly, they have a lot of cameras. We've got side cameras, rear cameras. Some of you already might have a few cameras that assist you in the parking, or surround cameras, inside the cabin camera, and then maybe infrared cameras, you know, cameras that you don't see, you know, the optic, you know, signals are out there, but they use a different spectrum, and they use it for maybe presence detection or gesture recognition. Like a friend of mine, he had his BMW, and he was showing me that he could just, you know, take his finger and circle in the air, and it would speed up to the next song that was playing on his dashboard. And then front camera systems that are used for maybe adaptive cruise control, or giving you collision warnings and things like that, or even cameras that can read objects in front of it. And all of these are actually sensors. As you can see, by positioning this all around the vehicle, it can provide 360 degrees worth of information to feed into a sensor. And that sensor looks like this. Remember our ECU? Well, now we have a new thing called Fusion ECU, or Fusion Electronic Control Unit, which is basically a, I'll show you a picture of this. If we did this in person, I actually have many physical hardware examples that I would pass out amongst the crowd, so you can touch it and feel it, how heavy it is and things. But I have a picture. But this is a bunch of computers that can take in all of these sensors, the radar, the LiDAR, the camera image sensor, left side, right side, and then the rear image sensor, and then integrate, fuse it all together so that it has a very good idea of what's out there, how is it changing every second, and actually take a decision. So at this point, I'm going to pause this, and I have to go to, let me just stop this here for a second. And let me change the computer audio. Oh, okay, I can do it right here. Share computer sound, and let me go back. And so the next slide is actually a little video of the earliest generation autonomous driving vehicle. That's the vehicle out here, and you can see all these barriers. So let me play that. So as you noticed, it knocked over that little orange cone. That was version 0.0. 3 years later, they've made several improvements, both in hardware and software. And this actually video is a colleague of mine who's actually driving inside that. And he's been working on it for the last 8 years or so on it. And he's based right here in Those are his hands at the top.
Okay. Car driving itself. I'm not touching anything. In the auto?
Those are his trousers, you can see below the steering wheel.
Auto. Still auto.
So that was I don't know how many of you might have looked closely, but that's actually a Ford Lincoln. My friend Bill, he actually went and bought that car straight from a dealership and then took that, I don't know, 5 years ago or 3 years ago, and they kept putting all this automotive driving. The only reason they bought it is that's the only car that had the maximum number of sensors at that time they could buy from the market, so they could test out some of their stuff. Now, that's not the only thing that's possible. Okay, let me move to the next slide out here so you can see. We saw what the car did from the outside. Let me give you a view of what the car or the computer electronics inside thinks it sees. So here we go. So there's no audio with this, but you can tell that this is actually in real time, the computer under different conditions, able to figure out where's the car, where's the pedestrian. It puts these little rectangular boxes around it. It can know street signs. It can tell landscape and trees. This video was shared by Audi, and they're using the same electronic software from the previous video. And then here, these circles are all your radar images or LiDAR images. The principle is the same. Notice as soon as it detects a pedestrian in front, it stops itself and stops again to let all these people pass. This is all being done by a bunch of computers inside. So this is what inside the computer, if you're sitting inside, this is what you would see, or the computer sees. Okay. So how does it do this? Well, this is an example of that hardware out there. And I have another picture of it, a little clearer, simply because of the dark background. But this is the software, these 4 layers of software. They're doing 3 things. The first one is perception. Let me just get that here. The first is perception, where it's taking all the sensors and immediately builds up the scenery outside and then does object recognition. So it knows, oh, that's a car here, that's a lane here, traffic sign up here, all of this it does. Then it does localization. Where is my position relative to all of these? And then the next thing it does, planning. That means the next second, how much speed should I have? How much steering should I control? How should I stay in the lane? So this loop of perception, localization, and planning, it does constantly. And to do all that, this is the software it uses. Drive PX is this actual hardware. Then there's an operating system. Then there's a bunch of what is called a software development kit, SDK. And then the Drive AV, this is something that the manufacturer, they can create their own on top of these 3. These 3 would be common, but the Drive AV would be customized to whatever car or truck or racing car or SUV or golf cart, whatever you have. That's what you put, so that it'll do these 3 things and you can customize that. And if you want to look inside that software, well, some of you might recognize this little penguin out here. It's actually running Linux inside. So here's your Drive PX hardware. It's a GPU with tons of processors and memory. And then you have this operating system or Linux. Then you have all this extra stuff. VisionWorks, a piece of software that can take the signals, convert it into visual objects. TensorRT is a machine learning software that learns as it goes along and remembers it. And then on top is all of your software. And then coupled with that is AutoSAR, so that you can talk to other computers inside of the car, like your safety systems and other devices. So this part is separate so that it can do external communication. This part is where it does all the autonomous driving stuff. Let me then quickly show you. This is actually the version 2. The earlier was version 1, Drive PX2. So you see out here, this is one processor. This is another processor. This has approximately 500 CPUs, and it's got a second one, and it's got this fan on top because it generates a lot of heat. And this is all the drive controller electronics. It looks pretty big. It's about slightly bigger than 8.5 by 11 sheet of paper and pretty thick. These blue little connectors are where you can put the wires for all the different optical, infrared, or GPS sensors. This is, of course, the familiar onboard diagnostics. So you can plug it in and it can talk to other parts of the car. So I'm going to skip this and now comes to the last few slides. So we talked about so many computers coming in and then so much software. Natural question, how much software are we talking about? So if you look at a fighter aircraft like the F-22, it has about 1.7 million lines of software. Contemporary or next generation F-35 Joint Strike has about 5.7 million. Boeing 787 aircraft has about 6.5 million lines of code. And then if you bought a high-end Mercedes Maybach, it actually contains 100 million lines of code. And these 100 million lines are actually running anywhere between 70 to 100 ECUs that are inside the body of that car. So this gives you an idea that the car is now a much more complex piece of machinery. The joke amongst us professionals is it's actually a computer with wheels attached, engines and wheels attached, or a data center with an engine and wheels attached. It's no longer a car. It's actually a mobile computer of sorts here. So clearly we do need more software just to run all of these. We also need good and better software. And that's something that is a skill that it's very hard to find people that can create good software. It takes an awful lot of talent, skill, money, and experience. And your modern day automotive companies, if you look at some of the job postings, there's more and more software attached automotive engineers that they're hiring. I myself actually teach a lot of little seminars on how to do software measurement, software management, as well as agile method, root cause analysis, and machine learning, because all of these are little techniques that you do need in this sort of stuff. So real quick, it's kind of natural to think that with so much computers and software, it's how does it change the cost of the car? Well, maybe 15 years ago, it was, I don't know, maybe 10% or less than 20%. But today, electronics is contributing 90% of the new features. I'm not saying the cost, but the new features. And so it takes a lot of time and effort to put all of that in. So clearly more and more software or electronics is becoming part of the fabric of the car out there. Here's a little graphic. So the cost share of the total cost. So we're now somewhere between 20 and 30%, or maybe a little over 30%, depending upon the model, of course. But it's projected by 2030, almost 50% of the cost of the car, usually because you want all those features. All those features require computers. All those computers require software. That's going to be a big portion of the price of the car. And now let me come to the last maybe 4 slides, but the overlooked aspect. Nowadays, we're talking a lot about battery electric vehicles and things like that. Not too long ago, this was not even an acronym that an automotive engineer knew. But despite the increase in electric vehicles, it's not yet mainstream. Certainly, if you do the math, hundreds of millions of cars, it's maybe 1 to 5%. I don't know, everyone counts differently, but it's not yet big. I have a quote here from my friend Mike Ramsey. He works for one of these market survey firms. he actually tells me that Tesla is a computer company trying to become an automotive company. And they're certainly, learning along the way. It took them a lot of time to figure out how to manufacture things and get other people to help them in it. And then they're changing stuff. And of course, they're doing things on the side as well. But the point here is that, if we're so hung up on battery electric vehicles and we want to be climate friendly, if tomorrow we converted all the cars to battery electric vehicle, where's the electricity going to come from to charge them? Some people actually did some calculation that we need several thousand megawatt power plants, and that would kind of defeat the purpose of fighting climate change, because those power plants, they'd have to burn something to produce that electricity. Those of you who are electrical engineers know we have transmission losses, so that's another problem. So we've got to be very careful about battery electric, but they use computers too, because they're putting in ECUs to manage the battery, make sure that it doesn't drain, it has time, redistribute the load amongst the different battery cells. So that's one area that actually is a lot of active work, a lot of software written to manage the battery inside electric vehicles. Now, the second thing, which is a little bit more closer to some of the stuff that I do, all the sensors inside your self-driving, quote unquote, self-driving car, well, they generate data. If you look at some of the data and plot it as a histogram, your camera itself, if it's running at 30 frames a second and not high resolution, 800 by 600 pixels, can easily generate like 3,000 gigabytes. Then your webcam and then your Velodyne LiDAR and several other things, if you add them all up, when you put that together, look at all of this. For each self-driving, fully self-driving car, okay, I should qualify that, it would generate 4,000 gigabytes of data each day. So imagine if we all had self-driving cars, the amount of data we're generating, where's it going to go? Who's going to store it? Who owns it? These are a lot of issues that still need to be resolved. That's why I call that the second deluge. Hasn't happened yet, but everyone can see it, and they're still trying to figure out how to deal with that. And then, of course, I would be remiss if I didn't talk about cybersecurity. The more the computers, the more the software, the more bugs and glitches and security potholes. Here, potholes will have a new meaning altogether. If you like, you can actually, SAE, I believe, puts out several publications on autonomous vehicle. This particular one is from March of 2018, because they highlighted something I talked about on the previous slide, which is all the data being generated by self-driving cars. But they have publications on various other aspects as well. So that brings me sort of just to the near end of my talk. I did want to mention that if those of you are interested, we run a embedded system workshop. Embedded systems is what we call ECUs, because they're embedded inside the vehicle. We've been running this for now about 17 years now. This year we're going virtual. You can check it out. We usually have anywhere from 180 to 200 people attend. All of these folks are industry professionals who create ECUs in different parts of the automotive. And there is a $5 fee, just to let you know. But you can see a little flyer out there, and I've shared one with Vatsala. Now, I like to always end my talk with a little bit of humor. So I'm just going to page through a few cartoons and let you all sort of digest that. So I like this one myself. Detroit meets Silicon Valley. And yeah, maybe in the future, your automotive mechanic might tell you to try and start your car, turn it off, start it again. Maybe that'll fix the problem. But at least it'll make the car repair bills a little cheaper. Okay, and then here's another one, which I think is particularly funny, where instead of waiting for the traffic lights to cross a road, self-driving cars will tell us when it's safe to cross so that they don't, run us down. Here's another one. I like this one, where you have a car crash, you can see these little cameras on top of each car and they've crashed. And I think that's a nice, good excuse that, it wasn't me, but the car was texting other cars. That's why we had this crash. And uh, I don't know how many of you, but you've seen at the back of these large trucks, how's my driving? Pretty soon it'll change to something like how's my programming? And you can call them and complain about it. Yeah. And here's another one, self-driving car. You ought to pay attention no matter how smart the car is. So and that's really important. And then finally, that brings me to the last slide. If you want to get connected with me, this would be, the way you can talk to me. So with that, I will stop sharing and thank you for listening, and I'll take any questions.
Sharan, that was a wonderful insight, and your expertise is beyond par. I am just glad that for the next driving license test, I don't have to attend it. Probably my car will. And thankfully, I am in the IT department. So those two takeaways. Muthu, you want to go over the questions?
Yeah, so
And,
if we, go ahead,
yeah.
Russell.
I would just like to thank all of you. In case you're getting late or whatever, if you have questions, I think Sharan would extend a little bit of his time to accommodate it. So please go ahead. And in case you were going to leave here, thank you so much. You've been a great audience. Thank you. Thanks a lot.
Yeah. All right.
Yeah.
So I see one question from Shrikant Agarwal. I'll read it out. Where do you think the automotive industry will be 10 years in terms of new technology, electric versus gasoline? That's a debate that we have maybe every year. And the most recent one was about maybe 1 month ago at the Engineering Society of Detroit. And there's a very good argument that we will still have gasoline engines. I don't think they're going to go away anytime soon, simply because, costs and invested infrastructure and, the automotive market is quite global. So not everyone can convert to electric. I mentioned the need for just a power generation to charge them. And electric still has a few challenges to overcome. One of the things I pointed out 20 years ago, that if you all became electric battery driven, how will you dispose of the batteries? Isn't that also an environmental threat? If you think about it, our battery technology is still the same chemical battery from 100 years ago. All we've changed is maybe instead of lead acid, lithium ion, but it's still a chemical battery. We need to come up with cheaper batteries, faster charging batteries, and also environmentally friendly batteries. The cost of recycling should not exceed that. So we still will see both electric and gasoline out there. Okay, the second question is, Venkat, is the use of ECUs in number and functionality going to be the same in ICE cars and EVs? Yes, I think it'll be about the same, because if you recall the 4 or 5 areas I talked about, they're dealing with the human, they're dealing with the safety system, they're dealing with connected vehicles. The electric car is only changing the combustion engine to an electric motor, but the rest of the car remains the same. So the number of ECUs in both number and functionalities is going to more or less stay the same. There's another one out here. Given that you have more and more ECUs, is heat and power an issue? Do automakers create custom silicon, Apple, Samsung, or they use off-the-shelf part? Well, more and more ECUs, heat and power is definitely an issue. the more computers you have, the more electricity it'll draw. And as a matter of fact, you can't even retrofit old cars with more ECUs because the alternator is incapable. The battery, lead acid battery, is incapable of powering them. So we do need more power, and we have to get rid of that heat. The only solution is more power efficient computers, like maybe a chip that's running your mobile phone. They're trying to look at that to replace that in future ECUs so they can partially solve it. And to the second part, do automakers create custom silicon? No, they don't create custom silicon. They might have off-the-shelf parts customized for them in the integration phase, but I don't see them asking for special silicon to be created. That's more likely to be the job of the semiconductor manufacturers. I did have a slide on who are the semiconductor manufacturers, but I cut it out because I didn't know if we would have enough time. The
Sharan,
other one, again,
Sharan,
yeah.
it's probably easier if Muthu asks you the question and you just can answer.
Sure. All right. Let me finish this one.
Okay, sure.
Okay. From Shrikant Agrawal, do you have any stats on accident reduction due to increased connectivity? No, we don't have any stats on that yet, because the connectivity is not yet, quite there. So Muthu, you can go ahead and start from Gandhi's question.
Sure. Yeah. After Srikant, there's a question from Ramesh Gandhi on security and hacking concerns and potential power outage of networks, GPS, etc. What will that do to the connected vehicles and safety in general?
Well, a short answer is it'll present a problem.
Sure.
And they have to solve the problem. There's no shortcut.
Great. Raj, next question. If flying cars are developed, will that be compact to accommodate all robust electronic controls? Airplanes are huge, and they could fit complete electronics needed for operation and safety systems. I don't understand what the question was, but maybe a comment.
Well, I think what he's saying, airplanes can accommodate all the, ECUs. Will flying cars do it? It'll have to be very, very, very compact and draw as little power. So whatever applies to regular cars will have to apply to flying cars. And it's still a ways away yet. I think flight cars will still be largely manual control, simply because of the safety aspects out there.
Great, thank you. Mahesh Reddy, next question from him. What technical challenges and issues are limiting auto industry to achieve level 4/5 ADAS or autonomy?
Okay, two things immediately come to mind. Number one, it's a very complex thing to achieve level 4 or 5. So the amount of software you need testing that software itself is a huge challenge. And that itself is problem number one. Problem number two might be even more important than problem number one. These self-driving cars have to coexist with humans who are driving the car. And how does it react to humans? Humans are unpredictable. It can't predict if the car in front of me with the human driver gets upset at me and tries to cut me off or do things. So we ourselves have a hard time coexisting. Human to human. Machine to human is an even bigger challenge. So we'd have to make the machine as smart or even smarter than the human. And we're not there yet. So we got a long ways to go before level 4 and 5.
Thank you. Next question from Amit says, how is the autonomy path different for trucking versus freight versus passenger cars? Very curious to know the difference in paths.
Yes, so there is some consensus in the industry that the trucking and freight might be a faster adoption of autonomous driving because they will stick to existing routes. They will operate within very, what you call, geofenced boundaries. And this would actually be more appealing because we do have issues like driver fatigue and things like that. So this would be actually a lot more helpful to increasing the productivity of trucking and freight. And again, they'll stick to well-known routes and not necessarily enter the city. So we're talking large freight, for example, picking up all the fruit and vegetables from a border post in Mexico and driving it all the way to a city in Texas. And that's it. It'll go to a loading dock, someone will unload, and then it'll drive right back. And so that might be a well-defined use case, and that might actually see more adoption of autonomous driving than passenger cars.
Thank you. Our own Jwalant from ACI here, Michigan asks, would you please share your thoughts on ROI point of view when it comes to the use of high-powered processors, along with the resources needed to develop SDKs and embedded software applications? Does this become challenging when the opportunities for reuse is limited across multiple vehicle platforms and OEMs?
So that's a pretty long question out there. It's actually a quite complicated. So there's no clear answer to that yet. But yes, we do have quite a bit of challenges there.
And next one from Ajay. There's only a couple of more, so thanks for staying late for us. How would you define electrification? When do you anticipate that there will be equal or more electric stations versus gas stations? Or will we see a decline in gas stations because electric cars can be charged at home?
I don't see an immediate decline of gas stations. And again, the question ought to be framed, what time frame are we talking about? 5 years, 10 years, 20 years? In the immediate 5 years, I don't see a decline in gas stations. I mentioned earlier the internal combustion engine, or ICE, as it's popularly, is still going to be around. And again, charging of electric cars, it takes quite a while, several hours to charge a battery electric vehicle. I don't really see, gas stations. They might have a few charging points for them, but maybe you park overnight or for 4 hours, 3 hours, something like that. So it'll be quite a while before we see that. What people are proposing is some sort of standardization in batteries. We don't have that yet, so that you can pull into a gas station, open the hood of your car, pull out your depleted battery, give it to the gas station, pay them some money, and take a fully charged, power pack, and then stick it in your car and then drive off. When that happens, then we will have a better answer to Ajay's question.
And some companies like NIO in China are doing something like this battery swapping, like as a service. So that's an interesting topic that's developing. Next one from Neelam is more of a comment, but it looks like in future, what is going to happen to driving license requirement if all this autonomy comes into play, I guess?
Well, I don't think driving license requirements will go away because, as you recall, in level 2, level 3, the human must be present in order to take over if there's a failure of the automatic driving system. So you'll still need all those skills. And then remember, they always want somebody to sue. So why give away that right? You can't sue a machine, and you can't sue the manufacturer of the machine. So the driver remains liable, and I think they'll still need revenue by charging you driver license renewal fees.
Sure. And the second question from Ramesh Gandhi himself, what level of redundancy are there to safeguard from hardware failure or software malfunctioning?
Yes, they do put in quite a bit of redundancy. Typically, the best redundancy is called TMR, triple multiple redundancy. So what looks like one system is actually 3 systems inside. one actually operating and two on standby. In case there's a glitch in one, then all three will take a vote and 2 out of 3 will win. But that gets very expensive. So we don't have very clear standards and regulations on that, and it will come sooner or later. So there's still a lot of work to be done there. But most people, they'll only put in a second backup system and only for what they deem to be critical.
Okay. Thank you. Amrish Chopra asked the next question. LiDAR was camera. It seems all automotive are using LiDAR except for Tesla. Do you see advantages/disadvantages between the two?
Well, when you talk to many of the suppliers here, like for example, Intrepid Control Systems, they recently relocated from Madison Heights to Troy. They're doing an awful lot of work. And when I spoke to them, and this I heard from several other folks also, the problem with LiDAR, it's very expensive. I don't know how much you know, but a typical LiDAR box is between $7,000 and $8,000 each. Tesla doesn't believe in that because their team feels they can do things differently and not add that extra $10,000 cost to their car. There are advantages to LiDAR, there's no doubt about it. And nobody depends on a single camera. If you recall my diagram just before the video, they fuse or integrate optical systems, infrared systems, GPS systems, LiDAR systems, regular LiDAR, and even millimeter wave sensors as well. So they don't depend on a single source like LiDAR.
Thank you. Just 2 more questions. So Krish asks, when will we see the flying car battery operated?
I don't know. You should ask a guy who has done flying cars before. I recall there was maybe some months ago at ASEI a flying car guy. So I do know that two weeks ago, someone in Japan did announce that they have a flying car and they're testing it. You can Google and look for it, but I think it'll still be a little while before that happens. I don't know, maybe 5-10 years from now, and again, limited as well. Because when you're talking about flying car, what's it called, that the regulatory body that controls airspace?
FAA?
Yes, Federal Aviation Authority. They'll have a lot to say about it.
Yeah, and we are aware of some flying cars. There was a Boston startup called Terrafugia, some company. They've done flying cars. I don't know how production and live they are, but there are a few companies out there that we are familiar. But of course, the regulations have to kick in.
Yes. And,
you know,
and I assume the question means when will you have flying cars is when can you go to your neighborhood dealer and say, I want that flying car. We're still
Uber flying car.
Uber has it. Okay, one last question before we kind of conclude. And of course, I didn't read out all the great comments and appreciations for your presentation. So one last question from Prashant says, advanced materials have been cornerstone of earlier innovations in earlier cars with focus on structures. Will that change with increase in ECUs or electronics and less of mechanical parts? And if so, what areas?
There might be some reduction of mechanical parts. In one of the earlier slides when I talked about safety systems, I showed in one of the diagrams the actuator. So you will still need actuators and mechanical components to do that. The reduction in mechanical would be when you, excuse me, replace the mechanical component with an electronically driven component. So like, linkages or things like that, they might disappear and you'll have an ECU on the spot itself which will have a small actuator that might operate the brake or things like that. Even the steering, you might still have what looks like a rotating column, but inside it would be maybe like a couple of coils that rotate and do sensing, and there is no steering column per se. Some cars even say do away with the steering and use a joystick instead. So there will be some reduction of components, but they will be certain mechanical components because after all, it is a mechanical device. The wheels will need to be there. The car door chassis, opening, closing them, you'll need mechanical components there. The engine, the source and power would be probably more electric. And if it remains gasoline, at least for the next 5 to 10 years, then you'll still have your pistons and crankshafts. So they will still remain there.
Thank you. That concludes all the questions. Thanks again for a great presentation. Vatsala, you are on mute.
You're welcome. Yeah.
Thank you so much, Sharan. Can't thank you enough for such a wonderful presentation. And thank you, audience. I know many of y'all have joined from India, so it's very late over there. Thank you so much for joining with us. If you have any additional questions or would like to connect directly with ASEI, you can go to our website, www.aseiusa.org. Thank you for your time and have a wonderful rest of the day. But before you go, don't forget, next Saturday, we are having another webinar of how to launch a successful engineering career. And after that, business continuity during pandemic. So stay tuned. You'll get emails with the information. Do log in. We welcome you always. Thank you.
Thank you.
Thank you.
Sharan
Thank you,
Thank you,
Vatsala.
Vatsala.
Thank you.
you.
Thank you so much.
Thank you, Vatsala.
Thank you so much for
Wonderful.
attending, sir.